Thank you very much. So I'm Neil Mitchell. I've recently moved to Barclays Bank and I'm hiring 9 functional programmers. So if after this you're thinking, wow, I'd love to do more Haskell commercially, come speak to me. So who saw the last talk by Tom? Okay, so most of you. So you'll remember Tom mentioned space leaks. So in this talk, I'm going to kind of give you the tools you need to fix the space leaks in your programs. And there are space leaks in your programs, you just don't know it. And so this GitHub URL has all the links and a lot more information about all the examples you'll see today. Okay, so before I go on to space leaks, I'll ask the question, should Haskell be strict? Unfortunately, there is a really good answer to this, and it definitely should not be strict. Several commercial companies have tried making strict Haskell. If you go and speak to people who've actually used strict Haskell, they will tell you that Haskell should definitely be lazy. So great, we know Haskell should be lazy. And why should it be lazy? Well, there are lots of really good examples of things you can do in a lazy language that don't work in a strict language. So you can compose functions. So in a lazy language, you just write OR of map, and that's all. Awesome. In a strict language, this doesn't work because you'll end up applying this predicate f to every item in the list before you find the first one that returns true. So strict languages suck. It also lets you, lazy languages also let you express this infiniteness. So you've got this zip 1 ... You've got the 200th prime number. So they just let you think about things in a far more natural and less kind of machine-constrained way. But what people don't always think about is actually, whenever we're programming using monads, we're probably relying on the fact Haskell is lazy. So if you ever see something like this, put strillen hello, error done. In a lazy language, that writes hello to stood out, and then errors out. In a strict language, this errors out immediately because this function ends up being strict in its arguments. So strict languages just don't work for things like monadic I/O, or you have to be a lot more careful. So all these things, I've taught hundreds of people strict Haskell and lazy Haskell. Everyone assumes Haskell is lazy, and then when they find it strict, they have to correct themselves and fix themselves. So Haskell should be a lazy language. And this is a great argument to make in a pub, but there is a problem. So let's sum a list. So this is a very simple Haskell function. So given a number and a list of numbers, it adds them all together. So if it's the empty list, we just return the number. If it's x cons x's, we add in the x and continue summing the rest of this. Very simple Haskell, looks nice, and we can print out the sum of 1 to 10. What's the peak memory usage of this function? Any ideas? What was that? O of n, exactly. So you would think we could sum up a list of the numbers 1 to 10 in one memory cell or constant memory, but it takes us O of n. And for the Haskellers, more advanced Haskellers, this is just a fold. So Tom gave us the very precise details of stack execution and heap execution. I'm just going to go for the Pac-Man level of how Haskell works. So if you had a strict language, you would create the list from 1 to 10, roll it all out in memory, and then you would kind of walk over it with a single memory cell containing, say, 15 once we'd consumed the first 5 numbers, and you would just kind of walk along it with some kind of cursor into the list or array, accumulating the value you're after. Well, that sucks because we had to allocate the whole array before we started. Okay. Ideally, you would leave the array kind of just as the beginning and the end. So even if this was 10,000 or 10 million, you would only just kind of hold on to the beginning and the end and only kind of pull off the elements as you needed them. And at the same time, you would be consuming them. So now we're nice O1 memory. The problem is in the obvious Haskell code, the thing everyone writes first, you're not consuming the numbers as you eat them, but you're just building up this big expression in your accumulator. So instead of kind of adding the numbers as you go, you're just taking the numbers off this one pile that you're producing lazily and adding them into this other pile that you're producing lazily. And then when you get to the very end, you have to walk down this pile all over again. So you end up using ON memory. So this is strict, this is bad. This is lazy, this is bad. And this is ideal. Unfortunately, Haskell is really just a lazy by default language. And if we just insert a single little exclamation mark here, suddenly we get the ideal behavior, and we only use O1 memory. Furthermore, if we actually run this through a compiler, it ends up going between 13 and 17 times faster. As soon as the compiler can kind of get away with all this, get rid of all this extraneous memory usage, it can do fantastic optimizations that basically reduce us to a few assembly code operations. So the meaning of this bang is essentially the same as using something like seek or like case that Tom used in the previous talk. This essentially says, at each step round the loop, force this value into its kind of evaluated form. So we just have this value left. And yeah, speed ups are fantastic. And if you're using Haskell and you've written your sum as a fold L, you can just switch to a fold L prime and your space leak goes away. So I've been looking at space leaks for a while after I managed to destroy some production code by introducing a space leak. So they're relatively rare. So I reckon there are maybe one space leak per 2,000 lines. But that does mean that in a large-scale project like GHC, there are probably quite a few space leaks. The other problem with space leaks is they're not really compositional. Code may always have a space leak, but there's a chance they'll have a space leak when you evaluate in a certain order, when you demand parts of the structure in a certain order. So you can't really look at some code and go, yes, that has a space leak, or no, it doesn't. The question is, does it have a space leak for you in the way you're using it? A space leak doesn't kill your program, but it certainly makes it go slower. It can make it use asymptotically more memory, and it can make it go orders of magnitude slower. So it's a very bad thing to have, but it's not quite as bad as fatal. It doesn't just kill the process. And I've maybe fixed 15, 20, 25 space leaks or so. They're not very difficult to fix. Once you're told this piece of code has a space leak, you can do all the things that Tom showed us in the previous talk. It takes like maybe 1 minute to fix the easy space leaks, and the really hard ones take like 2 hours. It's not a very difficult process. But the real problem with space leaks is that they're hard to spot, which means that all your code has space leaks. Very sorry to tell you this. So, given this list of issues, the real problem here is not space leaks. Space leaks aren't that big a deal. The real problem is they're hard to spot. And this talk gives you the easy way to spot space leaks in your code. And in my opinion, that means that the kind of one counter-exam argument for we should use strict is now gone, so we should definitely have a lazy language. Okay, so what's the simple trick? And the answer is limit the GHC stack. So this kind of simple trick came about when me and Tom were sat on a train and we were thinking, how would you detect space leaks in GHC? And we came up with some clever compiler infrastructure and some runtime system checks and some analysis passes on the GHC call stack. And then a few days later, I realized you could approximate, say, 75% of that with just the stack limit. So that's what we do. I tried it out. It works. And so this talk is really about how you take that idea, and this is the key idea, and turn it into kind of the tooling you can use to crank the handle and get rid of the space leaks in your program. So if you want an intuition, Tom's talk is probably described best. GHC uses the stack to kind of evaluate deferred pieces. So by limiting the stack, we limit how many deferred bits GHC can kind of consume. And then we spot the space leaks. And essentially, we turn the space leaks from being non-fatal into being fatal. And as soon as they become fatal, they're much easier to fix because the program blew up. You can look where it blew up, fix it blowing up, and now it's gone. Okay. So limiting the stack was the trick. This is the trick turned into a recipe of GHC command line arguments. So let's imagine we want to find all space leaks in a program. So we take our program, we compile it for profiling, just as normal. And then what we do is we start running the program on some representative data, our test suite, some relevant example. And what we do is we pass the plus RTS minus K 100K flag. And what this says to GHC is the stack is only allowed to be 100K. If any stack in the GHC program crosses that 100K, blow up. And if you take a normal program, pick something like 10, your program will probably blow up. So what you do is you increase or decrease that level till you find the threshold where above it, it succeeds, but below it, it fails. So now we know this program takes, say, 100 kilobytes of stack to run successfully. We then ever so slightly decrease that to, say, 99 kilobytes. So the program is now crashing with a stack overflow error. And now we add the flag minus XC, which tells GHC to print out a stack trace on every exception. So we've basically got our program to the point where it's crashing with a stack overflow on these space leaks, and it's giving us a stack trace so we can see where it was crashing with the stack overflow. Once you've got this, you just fix whatever problem it told you, try again with a lower number, and you just keep going until you can run, and most programs can run happily with a 1K stack. It isn't usually a problem. So what does the output of GHC actually look like in practice? Well, so I took our sum function, renamed it to sum1, and then compiled it and ran it through with a 100 kilobyte stack, and it spits out this. So this is me running the program, and you can see a call stack here that essentially says main caf, so the root of the program, main, the main function, and sum. So main called sum, and space stack overflow. So sum has the stack overflow. So now we know to go and look at sum. Sum's only 2 lines. And once you've had a bit of practice, it's kind of obvious where the space leak is. So the technique works, and it works quite well, and I found lots of space leaks with it. But before I kind of go off on the sales pitch for the technique, I should put in some disclaimers. So sometimes figuring out how to remove a space leak isn't trivial, because it's a property of more than just the piece of code that you're looking at. It's about how the code is evaluated. The other problem is that because we haven't been eliminating space leaks very long, as Tom says, it's kind of like one of the hard problems for Haskell programmers. There are lots of space leaks in all the libraries you're using, like the base libraries, Quick Check, the Pretty Printing library. They're everywhere. So when you find a space leak, it may well be in a library you're using rather than some code you're writing. Okay, so I thought, how do I test out these techniques? Well, Happy. Happy is a parser generator, so it's like an equivalent of Yak or Bison, but for Haskell. So it takes in a domain-specific language, which is kind of parser, production rules, and some embedded Haskell, and it spits out some Haskell. So I've had nothing to do with Happy until now. It was written by kind of Andy Gill and Simon Marlowe, so expert Haskellers, the original crowd, so it must be the best Haskell ever. It's an old, unfamiliar code base, and it's about 5,000 lines large. So it's not trivial, but it's also not a hunking great beast. So what I did is I picked one of the examples in their test suite, pretty much at random, called calculator.ly, and I ran happy over it with increasingly restrictive stack sizes until it blew up. And blow up it did. I found and fixed 3 space leaks, and now happy can be run on the calculator example with a 1K stack. So I know there are no obvious space leaks in reach from this technique anymore. 2 of them were trivial to fix, and I'll show those 2 in a second. One of them took about 2 hours to fix. So there was a case of an algorithm where the easiest fix was to rewrite the algorithm to make it simpler. And then it took like 2 hours to check it hadn't changed the behavior of happy. But so even on an unfamiliar code base, it wasn't that hard to fix the space leaks. So this is the first space leak. So can anyone figure? So I ran it. It said index 2. That's got a space leak. And can anyone spot the space leak? Yes, exactly. This I. So index into is essentially LM index from the standard library, and they always pass for the initial int a 0. So this code was probably written before LM index existed. And essentially it's a fold L-ish, yeah, pretty much fold L. And this accumulator here is going through, and it only gets evaluated when they actually get to the end. And if they never find the element in the index, you never evaluate it. So it's just a space leak. So that one was very easy. The fix for this is essentially stick a bang here, and it's all gone. Or switch to LM index, which doesn't have the problem. The second space leak was slightly more involved, but not much. So essentially, when you're generating the parser, you have conflicts, shift-reduced conflicts and reduce-reduce conflicts. And the way Happy deals with it is it builds up a conflict list, which is essentially a list of pairs of number of the first type, number of the second type. And all it wants to do is to print those to the user. It sums the 2 columns. And this was how it did it. So can everyone see the space leak here? Can anyone see the space leak? So essentially, they've used a fold L for a sum, which is never going to work. But it's actually slightly more complicated than that in this time. Only slightly, because they're summing over a pair. So the actual fix is to go slightly further. You need to use a fold L prime, just as a start. But actually, because your fold L accumulator is a pair, you need it to be a strict pair. Otherwise, you end up having a pair whose contents are still lazily evaluated. So it's just a case of, in code, you have to force the 2 additions before building the pair, and use the fold L prime, so it's all forced. So again, not very difficult to fix. And I dare say most Haskell programmers, if shown this code, would realize there was a space leak. The problem is you can't look at all 5,000 lines. You need kind of directing to the thing. Does that technique kind of make sense to everyone? Any questions at that point? Yeah, I would say very probably. But at the same point, I think I copied and pasted that out of the happy code. I may well have edited it for formatting or something. So maybe I fixed the bug. No, most probably I introduced a typo. Yes, you're totally right. Okay, so that is a kind of principled way to go about solving and detecting these space leaks, and it does work. Unfortunately, as I kind of said, me and Tom were brainstorming this kind of advanced runtime system plugin, blah, blah, blah. And then we found something that works 75% of the way. So this is kind of the bit where I say, well, actually, those 25% just make it a little bit more unpleasant than it would be otherwise. not impossible, but unpleasant. So we're using GHC's stack limits. And GHC's stack limits weren't really designed for this kind of analysis. So GHC doesn't always obey its stack limits. In particular, it seems that the main thread, the first thread, seems to get more stack, even if you say 1K. And if your code enters a masked block, like a finally or a bracket thing, it will ignore Stack Overflow when it's in that. So occasionally your stack grows too big, but it doesn't too much matter for this thing. One way you can get kind of back to the smaller stack is to fork a thread, run an mvar on that thread, and move the mvar back when you're finished. Essentially, a way to get off the thread you're on and get onto a fresh thread. And that will certainly, for example, fix the problem of the main thread getting too big a stack for this technique. The other thing is we use the -xc to print all exceptions in a Haskell program. I don't think many people ever do this because most Haskell programs, if you turn this on, are just spitting out exception after exception continuously. It turns out that in certain versions of the directory package, things like does file exist raise an exception if it's a file or a directory or things. So Haskell programs are throwing an awful lot of exceptions, and then furthermore, these exceptions are probably being caught and rethrown at multiple levels. So the output from XC can be incredibly verbose. Not a super problem. Pipe it to a log file and search through it later. The other problem is if your program eats asynchronous exceptions, you might end up catching the Stack Overflow exception and it not kind of bubbling up to the top. If so, you should probably stop your program catching async exceptions. It's not a good idea. So you can see the information, but the information is sometimes a bit garbled. The most confusing one for me, at least, is the stack contents. So GHC is producing, you can persuade GHC to produce a stack, but it's kind of designed for profiling rather than for this diagnostics. It's not really ideal for seeing the information we want to see. So in particular, the GHC stack elides adjacent duplicates. And when you've got a space leak, the thing that is really of most interest is the things that have adjacent duplicates. So it kind of throws away the information that you would have really liked it to preserve. The stack trace also doesn't go inside libraries. So if you've called the sum function in the base library and it has a space leak, you won't even see the function sum on your stack because it's in the base library. You'll see the function that called sum, and it won't say where it's going. So to fix that, I usually define a wrapper, just a function that returns itself, marked no inline so the compiler doesn't go in and remove it. And if you can take where you think the space leak is and start applying wrappers around pieces of it, then wrapper, because it's in your program, will show up on the stack trace, and then you can kind of get some more hints about where in the stack trace the problem is. So really, these techniques are about giving you a list of hints rather than a kind of actual pointer on a map. I also found that when diagnosing these things, it's useful to kind of start forcing things and unforcing things and seeing what happens. Does the space leak go away? Is this irrelevant to the space leak? What's going on? So I would suggest being familiar with the functions in something like the DeepSeek library, which do deep forcing of values. I usually define a fold-L prime that does a complete, not just weak head normal form, but full normal form evaluation on each step around the accumulator. This function, you can use things to kind of bounce onto fresh threads to get things fresh stacks. Okay, so the biggest weakness of the technique is false positives. So when thinking about this technique, I assumed that reverse would use a lot of stack because I was always told by the person who taught me Haskell that essentially reverse uses the stack to do the reversing. But it doesn't seem that actually that's the case. However, the mapm function does use a linear amount of stack in the number of elements. So if we take something like this program, so I've just put in the duration partly to make the stack trace a little bit more interesting. So we're mapm anything over a long list. If we run this with a restricted stack, we get this. And here we can see a few of those things, those warning signs I mentioned. So mapm isn't actually on the list because it's in the base library, but main is. And if we kind of experiment with putting things in and out of main, we find that actually it's mapm that makes a difference. Duration is, but it's as evaluated by, not really sure why. The calf occurs twice. But we can kind of see there is a stack usage problem in mapm. And the reason is essentially that if mapm is basically written as sequence composed with map, and if you tear into the guts of sequence, kind of looking through the I/O monad to how it's implemented internally in GHC, this is the code. And in particular, the thing that causes stack usage is doing evaluation inside a case scrutiny, and sequence makes a recursive call inside the case scrutiny. So that means that mapm does use a linear amount of stack and isn't really a space leak. So it's kind of the main false positive from this method. So what can we do about the fact that mapm uses a linear amount of stack? Well, in the previous example, we shouldn't have been using mapm at all. If you can, use mapm underscore, sequence underscore, or 4m underscore. It goes much faster. It eliminates this problem, has other benefits too. And if you use a tool like HLint, it will actually spot the places where you've incorrectly used mapm and then not looked at the value. In the specific case of the I/O monad, you can actually switch to a more efficient version of mapm. So I think there are about 6 different people who've had plays at writing more efficient versions of mapm, almost all of which don't have the linear stack usage. And in many cases, that's the reason they're a bit faster. So this blog post benchmarks them all. I wrote one, but it isn't the fastest. The other thing is, if you're using kind of maps in Haskell, you're very much talking about streaming data. Data is flowing in and flowing out continuously. You're thinking of like stream processing. As soon as you use something like mapm in the I/O monad, you're very much kind of reimposing sequential evaluation order on your code. You're doing this I/O operation on all the elements, and then likely as not, you'll do some other I/O operation on all the elements. That's not a very compositional way to do it, and it uses more memory than it sometimes needs to. So in many cases, if you're doing a large mapm, you're probably better off doing something like conduits or pipes and turning it into some kind of streaming I/O thing, demand-driven, pull-driven I/O. But it's still an annoyance, even after all that. Okay, so on to another example, a slightly more involved example. So Quick Check by John Hughes is way older than Haskell 98. And one of the things you can do is you can generate random values, random p's, and classify them. You can say, if p is greater than 0, then it's positive, else it's negative. And if you run Quick Check on this, it will classify the random numbers it generates. And so just a quick run, it says, in 100 test cases, we have 54% negative and 46% positive. Okay, nice feature. The problem is this feature, until very recently, had a space leak. So if you crank up the number of iterations, the number of things to check, very simple, just a single label, nothing fancy, then it completes all the tests, and then at the very end, it goes stack overflow, if you limit the stack size. So that in itself is a hint. Quick Check can run all these things, but when it comes to the end to kind of print the statistics to the user, it hits a stack overflow. that's another thing worth bearing in mind, is that actually this technique doesn't spot when you create a space leak. It spots when you evaluate a space leak. So the quick check was running along doing all its tests, creating a space leak, and only at the end when it went and evaluated it did we detect it with this technique. Okay, so if you do this technique, you get the stack trace out. You can see you fairly immediately led to the place where it accumulates these labels. Rather unsurprisingly, it has a map string int, which is for each label, the number of times you saw it. So roughly what you'd expect. And to combine different test runs, it uses union with plus. So if you think about the memory model here, we've got a map, and for each label, we've got an int. So where could we get a space leak? Well, there are two obvious places. Either the map itself could not be evaluated. So in memory, instead of having this nice small map, we have a list of union with, union with, union with, union with, union with, union with 1,000 times. Or we could have forced all those union withs, but the actual number inside the map, instead of being a nice single small int, is 1 plus 1 plus 1 plus 1 plus 1. So you can see from this data structure there are two possible ways we can get a space leak. Anyone want to guess which one quick check got? Any guesses? It was the second one. And in this case, you just switch the map type from being data.map to data.map.strict. I sent them a nice pull request, and quick check 2.8.2 fixes it. So this is important Haskell library, has had a space leak for probably forever, and it lay undiscovered, and it required ON additional memory and a bit of additional time, probably not too much. So the space leaks are out there. They're just waiting for you to find them. So other examples I found using this technique. So maximum buy in the base library. So when people destroyed the quality of the prelude by doing the whole foldable traversable nonsense, they also introduced a space leak in maximum buy, which I found. I tried the Alex Lexa generator. That had a lazy state monad, so it was accumulating a number in some state, but it wasn't forcing it. I tried the pretty library. So the pretty library is an interesting one. So the original pretty library, as written yonks ago, didn't have a space leak. And at some point, someone came along and decided they would make it faster. And so decided to sprinkle exclamation marks everywhere. And in doing so, they introduced a space leak. To patch the pretty, I just deleted some of the exclamation marks, which made it go much faster, use asymptotically less memory, be lazy as well. So I'm saying put some strictness annotations in your code, but do think. I've also, when developing Hugel and Shake, I've now switched to using -k1k in the test suite. So as soon as I introduce the space leak, I immediately find it and it fails the continuous integration. And I think there were 5 in Hugel and 1 and 3 in Shake. So this doesn't cover all types of memory usage. The one I've particularly focused on is the one that's specific to laziness. There are still memory issues with what would, I guess, be classically called lag, drag, void, and use, where you where you allocate memory much earlier than you need it, you hold on to it long after it's become useful. And these, the standard profiler will help catch. The other thing is it only finds the biggest space leak in your program, or the biggest map M. So you have to pretty much start by eliminating the biggest, and then you can drop the stack and try and find the next biggest. Okay, I have some GHC requests, but I will, yeah, I guess it would be nice if the GHC stack tracing the -XC on exception was a little bit more refined, if I could say which exception I care about rather than having all of them. And it would be nice if I had at least one level of call stack inside the library, so I knew I'd entered some in the library rather than just, just my function. And it would be very nice if there were repeat counts on the stack. So these are things that we could do, that someone might be interested in doing to refine the technique. But it's workable as is. So before I finish, I'll show you one final example. So I said at the beginning, I caused a production outage with a space leak. This is it. So Shake version 0.3 introduced a space leak. It went undetected for a year until various things got to the right point, and then things started failing in production, which was not fun, because that reduces the amount of time you have to fix it. And this cost about 1.5 gigabytes of memory on a 32-bit system, or essentially all the memory you had to give. You can see my nice little heap profile just kept going up and up and up as the build went along until it blew up. So I did all this before I had my space leak detection techniques, and I sent it through the standard GHC profiler, which is still a very useful thing to do, even with all these things. So if you compile your Haskell program, pretty much with the same profiling options as we were using for the space leak detection, you can also run heap profiles. And so if you in particular pass the magic HYXT, you can see what the memory of your program is doing. HY is ask for a profile based on the constructor, and XT is don't hide the thing that is taking up like a gig of memory because you think it might be a bit internal and I don't care. Always pass XT. And if you look at the heap profile for Shake blowing up, you can see this big, lovely purple line, which essentially zooms off until the program dies. And if you look at the legend, might be a bit too small to see, you can see this is stack. So the way you leak stack in a Haskell program is either you have a lot of simultaneously running threads, or you have a lot of dead threads that are finished, but you've kept a hold of their thread ID. So a little bit of augmentation told me it definitely wasn't the first. So all I had to do was look for some thread IDs I was keeping alive. And I found some. So Shake has a thread pool. And in that thread pool, I kept a list of the running threads. So the list of running threads is only there so when there's an exception, I can go and clean up properly. So under normal circumstances, I wasn't forcing it or looking at it. All I did is when I spawned a thread, I put it in the pile. And when a thread finished, I took it out of the pile. So I was creating a perfect space leak of just a list of updates to this set, to the empty set. And because I never actually used this set until there was an exception, or in some cases never, I was keeping a handle to all the stacks. The fix was trivial. I just insert a bang here, but took a very long time to find. So space leaks, they're usually not fatal, but if you hit the right memory limits, they can be. And yeah, it's only often a one-character fix, but this scarred me for life and led me to standing here talking about space leaks. Okay, so finally I'd like to end with a call to arms. So Haskell has a notorious reputation for having space leaks. And we didn't know where they were, and they were everywhere. And they still are, but now I think we actually have enough of the tools to find them and fix them, and we can stop being laughed at for the people with space leaks. It's also a great way to get into a new project. Get the code, do this stuff on it, you'll find some space leaks. They're nice meaty patches. The maintainer will be very happy to get the space leaks finished. I would also encourage you to add -K1K to all your test suites so that we don't reintroduce them. And hopefully, with a bit of time and a bit of effort, this can stop being kind of the embarrassment to the Haskell community. Thank you very much.
Does anyone have any questions? So you mentioned an example where you introduced space leaks by adding strictness annotations.
Yeah.
Could you elaborate on that a bit?
So essentially, in the printing combinator library, they've roughly built up an AST of the things that have been requested. They put exclamation marks in the AST. So where it should have been lazily constructing the beginning of the AST and immediately the pretty printing renderer consuming it and printing something out, instead, that exclamation mark was forcing down the entire data structure, so the entire AST had to be in memory. So in some cases you need it, but in this case, if you just did a list of characters, it was forcing the whole list of characters before printing out the first one, which was easy.
Do a lot of these problems just go away if you use the compiler optimization flag, or is this after you've had that?
Some do go away after compiler optimizations. So I found one bug in Alex where a GHC rule was fixing a compiler optimization. So I was expecting the initial sum example that I showed to go away under O2, but it didn't. Don't know why. So certainly you can debug for space leaks with this technique using O2 as well, to care about only the ones that are left after O2, or without O2 to debug all of them. I would encourage you to look for all of them, because the compiler one day, the compiler can be very sensitive about not managing to reduce the space leak. It actually isn't nearly as good as I was expecting it to be. I'm sure the sum example used to be hit by strictness analysis at some point.
Unfortunately, we don't have time for any more questions. If you want to grab Neil afterwards, you can do so. Can we get a round of applause, please?